Here we have a calculus problem on infinite series. Okay, let's go to the information. Use a sequence of partial sums to determine whether the series converges or diverges. So here we have an infinite series and we have to check whether this series converges or diverges using the sequence of partial sums. Okay, for that, first we have to write the nth term of the given series, that is n positive 1 over n. Okay, now let me find the first partial sum, that is S1. So first partial sum is nothing but the sum of first one term of the series. Sum of first one term is nothing but the first term of the series. To get the first term, what I have to do is I have to plug in n equals to 1 into the nth term of the series. When I plug in n equals to 1 over here and here, I'm getting 2 over 1 because 1 plus 1 is 2. 2 over 1 is just 2. I'm getting S1 equals to 2. Okay, now let me get the second partial sum. To get the second partial sum, what I have to do is I have to add the first two terms. Already we know the first term, which is 2. Now I have to add the second term. So to get the second term, I just have to plug in n equals to 2 into the nth term over here. When I plug in n equals to 2 over here, 2 plus 1 is 3. 3 over 2. Now let's get the third partial sum. To get the third partial sum, I have to add the first three terms. Already we have the first two terms, 2 positive 3 over 2. Now to get the third term, I have to plug in n equals to 3 over here. When I do so, I'm getting 4 over 3. Okay, now let's find the fourth partial sum. So for that, we have to add the first four terms. We have three terms over here. The first three terms, 2 positive 3 over 2 positive 4 over 3. Okay, to get the fourth term, I have to plug in n equals to 4 over here. Then I'm getting 5 over 4. Okay, now what I have to do is I have to form a sequence with the partial sums what I got over here. That is S1, comma S2, comma S3, comma S4, and it keeps going. Okay, so if the sequence with the partial sum converges, then the given infinite series also will converge. In case the sequence with the partial sums diverges, then the given infinite series will diverge. So now we have to find whether the sequence with the partial sums over here converges to a finite value or diverges. So how do you have to find that? So for that, we have to look at the pattern we have over here. So particularly look at the pattern in the fourth partial sum, because only in the fourth partial sum S4, we have more number of terms compared to the other partial sums S1, S2, S3. Okay, now let's look at the first term over here. It's 2. And what is the value of the second term? 3 over 2. So we know that it's 1.5. And what is the value of the third term? 4 third. It's approximately 1.3. So, and what is the value of this 5 fourth? It's approximately, so not approximately, it's exactly 1.25. Okay, so when I evaluate the value of each term in the fourth partial sum, so I'm getting 2, 1.5, 1.3, and the last term, the value of the fourth term is 1.25. Okay, what if I find the 10th partial sum or 100th partial sum? What will happen? So if I find 10th partial sum, so I'll write first 9 terms, and the 10th term will be, to get the 10th term, what I have to do is I have to plug in n equals to 10 into the nth term, then I'll be getting 11 over 10. So what is the value of this 11 over 10? It's 1.1. So this is also close to 1. So like when I evaluate the partial sum in each partial sum, so the value of the last term is getting closer to 1. So when I find the value of the last term of the fourth partial sum, it's 1.25. So when I find the value of the last term of the 10th partial sum, it's just 1.1. So what if I find 100th partial sum? So the last term will be the 100th term. To get the value of the 100th term, we have to plug in n equals 100 into the nth term of the series. That is when I plug in n equals 100 over here, I'm getting 101 over 100. Its value is 1.01. So here in the fourth partial sum, the value of the last term is 1.25. In the 10th partial sum, the value of the last term is 1.1. In the 100th partial sum, the value of the last term is 1.01. So it's getting closer and closer to 1. So for example, even if I evaluate the sum of infinite terms in the given infinite series, what will happen? So like the first term I'll be getting 2, the second term I'll be getting 3 over 2, the third term I'll be getting 4 over 3. In this way it will keep going. So here this time I'm trying to find the sum of infinite terms. So definitely when I plug in n equals to infinity over here, so I'll be getting 1 as the value of the last term. So when I evaluate each partial sum, so the last term of each partial sum is getting closer to 1. So in case when I evaluate each partial sum, if the value of the last term is closer to 0, then I can say that there is a chance for this series to converge to a finite value. But here, when I evaluate each partial sum, the value of the last term is getting closer and closer to 1, not 0. So whenever the value of the last term in each partial sum is getting closer to a value which is other than 0, then we can say there is a chance for the given infinite series to diverge. So we get some initial idea that the series may diverge because the value of the last term in each partial sum is getting closer to a value 1 which is other than 0. So that's why I'm saying there is a chance for the given series to diverge. How do we have to conclude the given infinite series diverges? So for that, let's consider the sequence of partial sums of over here. So if the sequence of partial sum diverges, then we can say that the given infinite series diverges. So for that, what we have to do is we have to write an inequality, that is Sk greater than k times A. So here this Sk is the kth partial sum and here is some constant. Okay, so the sequence we have over here satisfies this inequality. We can say that the sequence we have over here with the partial sum diverges, then the given series also diverges. Okay, so how to check whether the sequence of partial sum satisfies this inequality Sk greater than Ka? So usually we check whether the sequence satisfies this inequality from the second partial sum, that is from S2. Okay, now for that we have to evaluate the value of S2. So the value of S2 is equal to 2 positive, the value of 3 over 2 is just 1.5. Then when I add them, I'm getting 3.5. So here I'm getting 3.5. This value is greater than the first partial sum 2. That means the second partial sum S2 is greater than 2. So now since as I said already, usually we check this inequality only from the second partial sum S2. So now let me plug in K equals to 2 over here. Then I'm getting S2 equals to 2A. Already we know that S2 is greater than 2. Since S2 is greater than 2, this value of 2A must be equal to 2. So then let's solve for A. For that we have to divide both sides by 2. Then I'm getting A equals to 1. Okay, now we can rewrite this inequality as S2 greater than 2 times 1. Okay, now let's verify the third partial sum with the inequality over here, that is S3 greater than, so since I plugged in 3 for K over here also I have to plug in 3 for K, and already we know the value of A, which is 1. So the 3 times 1 is just 3. That means that the third partial sum S3 has to be greater than 3. So let's check this over here. So we know that the first value, the first term is 2 over here, and the value of this one is 1.5. The approximate value of this 4.3 is 1.3. So when I add these 4 values, so it's greater than 3. So the third partial sum satisfies the inequality we have over here. Okay, now let's check whether the fourth partial sum satisfies this inequality. For that we have to write S4 greater than, so here also we have to plug in 4 for K times the value of A is 1. So the fourth partial sum S4 has to be greater than 4. Let's verify this. So here we have 2, positive 1.5, positive 1.3, and the value of 5 over 4 is 1.25. When I add all these 4 values, definitely it's greater than 4. So the fourth partial sum also satisfies the inequality over here. So clearly the sequence of partial sums over here satisfies the inequality Sk greater than Ka. So therefore the sequence over here diverges. Since the sequence of partial sums diverges, the given infinite series also diverges.